Hello and a very warm welcome to you students. So what are we going to learn today? We have done enough on equation. Let's today study one of the most interesting chapters of mathematics, that is permutations and combinations. Now what makes it special is the wide application of these techniques in our day-to-day life. This chapter also forms the basis of probability and the chapter on binomial theorem. So students, tighten your seat belts and get ready for a wonderful learning. So students, consider three boxes. Let's say they are A, B and C. A has got 3 red balls numbered 1, 2, 3. B has got 4 green balls 1, 2, 3, 4. And the box C has got 5 green balls 1, 2, 3, 4, 5. Now, if I ask you, in how many ways can you select any ball? Then what's going to be your answer? Now if I say you have to select 2 balls, then what's going to be your answer? And if I twist it, that the balls are identical, that is red balls are identical, green balls are identical and the blue balls are also identical, then how you are going to select 2 balls out of these balls? Now this is going to be very tricky. Now let's consider this boy who has a habit of tossing coins. So let us say that he tosses the coin once. Now a coin has got 2 sides, heads and tails. If I ask you what are the outcomes possible if he tosses the coin once, then definitely your answer is going to be either it's going to be heads or it's going to be tail. So there are actually 2 outcomes. Now we take the same boy and this time he tosses the coin twice. What are the possible outcomes this time? After thinking, you can definitely say that the total possible cases are heads, heads, tails, tails, heads, tail and tails, head. Thus, there are 4 cases this time. Let's say the boy is very much obsessed about tossing the coins, and what he does this time is he tosses it 3 times. Now after tossing it for 3 times, if I ask you what are the possible outcomes this time, then what is going to be your answer? Yeah, there are actually 8 cases this time, and they are heads, 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 tails, 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 heads, tails, tails, heads, heads, tails, tails, head, tails, tail, tail, heads, heads, tails, head and tail, heads, heads. So in all there are 8 cases. But what if I say the same boy tosses the coin for 15 times or maybe 20 times? Are you going to write it on a piece of paper and try to know all the possible cases? No. What you are going to do is use the mathematical techniques of counting, which we are going to study in this lecture. Now, what do we mean by the term counting? Counting refers to the application of mathematical techniques to know the size or count of a finite set. Now what is a finite set? It is a set in which the number of elements can be known or counted. Now counting can be that of number of trees in a garden, number of balls that can be placed in a room, or even finding the integer solutions of the equation x plus y equal to 10. So what we see is we do counting all the time. You may count the number of footsteps you take from your home to reach your school, or I may even count the number of apples in my refrigerator. Thus what we are doing is we are counting all the time. So let's try to put some more light on the topic counting. Now let's look at the 2 principles of counting. The first one is the addition principle, and it states that if we have 2 sets K1 and K2 with the property that K1 is a subset of K and K2 is also a subset of K. Also we have K1 intersection K2 is equal to 0, that is K1 and K2 do not share any common element, and K1 union K2 is equal to K. Then we must have the number of elements in K equal to the number of elements in K1 plus the number of elements in K2. Such subsets of K are called mutually exclusive and exhaustive sets. Now what is a mutually exclusive set? If two sets do not have any common element, then they are called mutually exclusive sets. So we try to put it in simple words. What we can say is that if we have a task that can be performed in m different ways, and let's say we have another task that is independent of the first task and can be performed in n different ways, then either of the two tasks can be done in m plus n number of ways. Now let's try to understand the addition principle through an example. From a deck of 52 cards, in how many ways can we pick a card such that it is either an ace or a king? So what we have to do in this problem is we have to find the number of ways in which we can pick a card, and that can either be an ace or a king. So I know you guys must have had wonderful sessions of playing cards, but for those who don't have any experience with it, let me tell you that in a deck of playing cards, 52 playing cards, we have 4 aces, that is ace of club, ace of diamond, ace of spade and ace of heart. And similarly we have 4 kings, king of club, king of heart, king of spade and king of diamond. Now let us say that K1 is equal to the set of aces in a playing card, and K2 is a set of kings again in a deck of those similar playing cards. Now let us say that K is equal to the number of ways in which we can pick a card that is either an ace or a king. So according to the addition principle, we have K is equal to K1 plus K2. Here K1 intersection K2 is equal to 0 because it is not possible for any card to be an ace or a king at the same time. So K is equal to K1 plus K2, and that is equal to 4 plus 4, and that is again equal to 8. So what we see is the number of ways in which we can pick a card such that it is either an ace or a king is equal to 8. Let's look at the second principle of counting, that is the multiplication principle. It says that the multiplication rules says that if a finite set K can be written as K1 cross K2 for some sets K1 and K2, then cardinality of K is the product of cardinalities of K1 and K2. That is, cardinality of K1 cross K2 is equal to cardinality of K1 into cardinality of K2. Now what is cardinality? Cardinality is nothing but the number of elements in a particular set. Now this sounds a bit complicated. Let's try to see it through simple words. If a task can be performed in m different ways and its subsequent task can be performed in n different ways, then the two tasks can be performed in succession in m into n number of ways. Let's look at an example. If there are 6 ways to go from A to B and there are 5 ways to go from B to C, then find the number of ways to reach from A to C. So what we have is, we have got 6 ways to go from A to B, that is, and we have 5 ways to go from B to C. Now let us say that K1 represents the number of ways to go from A to B and K2 represents the number of ways to go from B to C. So K1 is equal to 6 and K2 is equal to 5. So what we have is K, that is the number of ways going from A to C, is equal to cardinality of K1 into cardinality of K2, and that is equal to 6 into 5, and that is equal to 30. So the number of ways to reach C from A is equal to 30. Okay, now let's try one more problem. Find the number of 5-digit numbers that can be formed from the digits 1, 2, 3, 5, 7, 8 and 0. Now in this problem we have to find the number of 5-digit numbers from the given digits. These are the digits, but it is divided into 2 parts. In the first part we have the condition that the digits can be repeated, and in the second case the digits cannot be repeated. So let's try to see and solve this problem. Let's consider the first case, that is digits can be repeated. Now the digits are 1, 2, 3, 5, 7, 8, 0. So what we have to do is we have to form 5-digit number using these digits, and the cases digits can be repeated. Now any 5-digit number is of the form this. We have got 5 places to fill, and the condition is digits are repeated, but we know that 0 cannot fill this first digit. Any 5-digit number cannot have 0 at its first place. So what we see is we are going to find and try to look at how we can fill these 5 places, these 5 digits. Now the first place we cannot have a 0. So what we have left is these 6 numbers. There are 6 ways to fill this place. Now the second place, in the second place we can have a 0. So, and also digits can be repeated. So whichever digit is occurring at this first place can also occur at the second place. So in all we have how many? 7 number of ways. So this place can be filled in 7 number of ways. Again the third place. Third place can also be filled in same number of ways, 7 ways, because digits are repeated. And so the fourth place and the fifth place. So what we see is we can fill the first place in 6 number of ways, second place in 7 number of ways, third place in 7 number of ways, fourth place in 7 number of ways, and fifth place also in 7 number of ways. So in all the total number is equal to 6 into 7 into 7 into 7 into 7, and that is equal to 6 into 7 to the power 4. Again I would like to repeat, the first place can be filled in 6 number of ways because we cannot have a 0 at the first place. The second place can be filled in 7 number of ways, and so the third, fourth and the fifth place, and so the answer becomes 6 into 7 to the power 4. Now let's try to solve the second part of the problem, that is the digits cannot be repeated this time. So what we have is the digits are 1, 2, 3, 5, 7, 8, 0, and any number of 5 digits is of this form. Now we are going to see how we are going to fill all these 5 places, but with the condition that digits cannot be repeated. Now what we know is we cannot have 0 at the first place, that is at this place we cannot have 0. So what we are left with? We are left with the remaining 6 digits. Now for the second place, again we have got 6 choices, because 0 can be filled in this place, and if for example 1 is placed here, then we cannot have 1 at this place, at this place, at this place, or at this place. So for this second place, how many ways we have got? 6 ways. For the third place we have got 5 ways, because the 2 numbers that have been filled here cannot be filled in this position. So what we are left with? 5 number of ways for this position. Similarly for this position we have 4 ways, and similarly for the last or the units digit we can have 3 number of ways. That is, the first position can be filled in 6 ways, second in 6 ways again, third position can be filled in 5 ways, fourth in 4 ways, and the last, that is the unit digit, can be filled in 3 ways. So the answer becomes 6 into 6 into 5 into 4 into 3, and that is equal to 2160. Now again what we have done is we have used the multiplication rule, and these are number of ways to fulfill these places. So what we have done is we have used the multiplication principle to arrive at the answer. After studying the multiplication and addition principle of counting, it's time for us to understand the concept of permutation. Permutation refers to the different number of arrangements made by taking some or all of the things from a set of things. It means that we are going to consider number of arrangements here, and it represents the total number of arrangements when we take some or all of the things from a set of things. It is denoted by NPR, and this is equal to n factorial divided by n minus r factorial. Now what is a factorial? You must be wondering what this term has come from. Factorial n, it is nothing but equal to n into n minus 1 into n minus 2 up to 3 into 2 into 1, or in other words we can say that it is the continuous product of all the consecutive natural numbers varying from 1 to n. Now NPR is the number of permutations of n different things taking r at a time. It is also denoted by Pn comma r. That is, n is a total number of things and r is the things we are going to permute. Now NPR is equal to n factorial divided by n minus r factorial. Now let's try to expand this thing. We know that n factorial is equal to n into n minus 1 into n minus 2 up to 3 into 2 into 1. And what is n minus r? N minus r is a continuous product of consecutive natural numbers from n minus r to 1. So that becomes equal to n minus r into n minus r minus 1 up to 3 into 2 into 1. So these terms n 3 to 1 up to n minus r gets cancelled out, because these terms will also be appearing on this term, because r is less than n. So it ultimately reduces to NPR equal to n into n minus 1 up to n minus r plus 1. Once again see what is permutation. It is the different number of arrangements by taking some or all of the things from a set of things. It is also denoted by P n comma r, and it is a permutation of n different things taking r at a time. Here important thing to note is that n things are all different. Now it is equal to n factorial divided by n minus r factorial, and n factorial is nothing but equal to n into n minus 1 up to 3 into 2 into 1, or in other words we can say it is the continuous product of consecutive natural numbers varying from n to 1. And so NPR is equal to n factorial divided by n minus r factorial, and that is equal to, when we solve it, becomes n into n minus 1 up to n minus r plus 1. Now some of the important points to remember regarding permutation are: np0 is equal to 1, np1 is equal to n, npn minus 1 is equal to npn, and that is also equal to n factorial. This last one is very important. Npn is equal to n factorial. Now npn represents the total number of arrangements of n things from a set of n things. That is, we are taking all the things and we are going to arrange them, and this is done in n factorial ways. Also n minus 1 pr is equal to n minus r into n minus 1 p r minus 1, and also npr is equal to n minus 1 pr plus r times n minus 1 p r minus 1. Now these are some of the very important points, and it's very good if you can remember them. Also we have left this as an exercise for you to prove it, and we are going to apply all these points and all these properties later on and while solving some of the problems. Now let's try to solve a problem. Find the number of arrangements where 4 people can be seated in 6 different chairs. Now what we have to do is we have to find the number of arrangements where there are 4 people and they have to be seated in 6 different chairs. Now the number of chairs is equal to 6 and the number of people is equal to 4. So what we can say is, here n is equal to 6 and r is equal to 4. So total number of ways is equal to 6p4, and that is equal to 6 factorial divided by 6 minus 4 factorial, and that is equal to 6 factorial divided by 2 factorial. Now 6 factorial is nothing but 1 into 2 into 3 into 4 into 5 into 6, and that is equal to 720, and 2 factorial is equal to 2 into 1, and that is equal to 2. So 720 divided by 2 is equal to 360. So the number of ways in which we can have an arrangement of 4 people around 6 different chairs is equal to 360. When we were discussing about the formula for permutations, we emphasized that there are n different things. Now let's take a situation where we have n things, but out of those n things there are few things which are alike or which are similar. Then how does it change the scene? How does it change the number of permutations? Yes, in fact, the number of ways or the number of arrangements in this case changes. And how it happens, let's see it. The number of permutations of n things taken all at a time when P are alike of one kind, Q are alike of another, R are alike of another, and the rest of all are different. So in this case it is equal to n factorial divided by P factorial into Q factorial into R factorial. So what we have here is, we have got n things and we are going to take all of those things and permute them. But the condition here is, we have P things that are alike of one kind, Q things that are alike of another, R things are alike of another, and rest of the things are actually different. So the number of permutations in this case become equal to n factorial divided by P factorial into Q factorial into R factorial. Let's try to go through an example and this will clear this concept. Find the number of arrangements of the letters of the word Constantine. Now here the total number of letters is equal to 11. Number of n is equal to 3 and the number of t is equal to 2. Also the number of different letters is equal to 11 minus 3 plus 2, and that is equal to 6. So the total number of arrangements is equal to 11 factorial divided by 3 factorial into 2 factorial, because 3 factorial is number of n that are similar. We have got 3 n's in this word and the number of t is equal to 2. So by the formula n factorial by P factorial into Q factorial into R factorial, we will get that total number of arrangements is equal to 11 factorial divided by 3 factorial into 2 factorial. Now students, it's time for us to solve an IIT problem. This problem appeared in IIT JEE 2009 and it is as follows. The number of 7-digit integers with the sum of the digits equal to 10 and formed by using the digits 1, 2 and 3 only is option A is 55, option B 66, option C 77 and option D 88. So in this question what we have to do is, we have to find the number of 7-digit integers and the condition here is, the sum of digits is equal to 10 and is formed by using the digits only 1, 2 and 3. So how to solve it? Let's go through the solution of it. The digits are 1, 2 and 3 and what we have to do is, we have to find all the 7-digit numbers that can be formed from these 3 digits. But the constraint here is, the sum of the digits has got to be equal to 10. Now when we analyze it, we just see that there are 2 cases. Case 1, that is, we have got 5 1 and 1 2 and 1 3. And the second case is, we can have 4 1s and 3 2s. That is, in the first case we have got 5 1s, when we add them plus 2 plus 3 will be equal to 10. And in the second case again we have got 4 1s plus 3 2s, and when we add them then it becomes equal to 10. Now when we look at the first case, the number of ways in which these digits, that is 5 1s, 2 and 3 can be arranged is equal to 7 factorial divided by 5 factorial. Why? Because 7 factorial is because of we have got 7 digits and 5 factorial is because we have got 5 1s and these 5 1s are identical. So total numbers is equal to 7 factorial divided by 5 factorial and that is equal to 42. By the second case, we have total numbers is equal to 7 factorial divided by 4 factorial into 3 factorial. 4 factorial because there are 4 1s and which are again similar, and 3 2s which are also similar. So the total numbers becomes 7 factorial divided by 4 factorial into 3 factorial and that is equal to 35. Hence we can say that the total number of such 7-digit numbers using only the digits 1, 2 and 3 and whose sum is equal to 10 is equal to 42 plus 35 and that is equal to 77. So what we can say is the correct option is C. Once again what we have done is we have considered 2 cases. If we have 5 1s and 1 2 and 1 3, and in the second case we have got 4 1s and 3 2s. So according to the first case, total numbers is equal to 7 factorial divided by 5 factorial and that is equal to 42, and according to the second case total numbers is equal to 7 factorial divided by 4 factorial into 3 factorial, and that is equal to 35. So the total number of such numbers become 42 plus 35, and that is equal to 77, and which is the third option. Now students, let's look at another problem and which appeared in IIT-JEE 2007. The letters of the word coaching are permuted and all the permutations are arranged in an alphabetical order as in an English dictionary. The number of words that appear before the word coaching is option number A 360, option B 192, option C 96, and option number D 48. So what we have to do is, in this problem we have the word coaching and all the letters of this word, that is COCHIN, they are permuted, and then all those words are arranged in an alphabetical order as it would appear in English dictionary. So what we have to do is, we have to find the number of words that will actually appear before the word coaching according to an English dictionary when they are arranged in an alphabetical order. Now this is a very interesting problem that appeared in IIT-JEE, and it will clear some of the very fundamentals which we have explained to you earlier in this lecture. So let's try to visualize it. The letters of the words are COCHIN. Now if we are going to arrange all these letters in an alphabetical order, the order of the letters will be C, H, I, N, O. That is, O will appear at the last. Now when we permute or when we write all the words with these letters, then the words will start with C because it's the first letter. Now the second position or the second place will be filled by C, and the remaining 4 positions will be actually filled by the remaining 4 letters. Now we can permute all the 4 letters in 4 factorial ways. Therefore the number of words that have C at the first place and C again at the second place will be equal to 4 factorial. Now the second case, the second position gets filled with H. Now the 4 places will be filled again by the 4 letters, and they can be permuted among themselves in 4 factorial ways. So the total number of words is equal to 4 factorial. Similarly, when I gets placed at the second position, the number of words formed are 4 factorial. And when N gets placed at the second position, the number of words is equal to 4 factorial. Then the next letter that is going to appear at the second place is O. So what we have is, the second place gets filled with O. Now the third place will be filled with C, the fourth with H, and the fifth with I, and last the sixth place will be filled with N. So what we see is, the very next word that will appear is coaching, and that is the required word we need. So the total number of words before coaching is equal to 4 factorial plus 4 factorial plus 4 factorial plus 4 factorial, and that is equal to 24 plus 24 plus 24 plus 24, and that is equal to 96, because 4 factorial is equal to 24. Hence what we can see is, the correct option is C. Now let's see another solved problem that will help us to enhance our clarity on the concept of permutations. Find the number of permutations that can be obtained for the word bracket for A. Vowels occupy end positions, B. Vowels are always together, and C. T occupies the fourth position. What we have to do in this question is, we have to find the number of permutations for the word bracket, and we have 3 cases. For 3 cases we have to find the number of permutations. The first case is vowels occupy the end positions, second is vowels are always together, and the third one is T occupies the fourth position. Now let's go through the solution of it. The given word is bracket. Now let's see the first case, that is vowels occupy the end position. Here in the letters of the word are B, R, A, C, K, E, T, and the vowels are A and E. 2 vowels we have. Now the condition says vowels should occupy the end position. So the word could be arranged in this way, A being the first letter and E being the last one. It can also happen that E is the first letter and A is the last letter. So we have 2 ways of doing it. Now the middle letters can be arranged in 5 factorial ways, as 5p5 is equal to 5 factorial, and also A and E can interchange their positions, that is A can take the place of E and E can take the place of A. So what we can say is the total number of words is equal to 5 factorial into 2 factorial, that is equal to 120 into 2, and that is equal to 240. Once again, the two vowels are A and E, and they have to occupy the end position. The middle 5 letters can be arranged among themselves in 5 factorial ways. Also we can say that A and E can interchange their positions, so that the number of ways is 2. So the total number of words become 5 factorial into 2 factorial, and that is equal to 240. Now let's look at the second case, vowels being together. Again the vowels are A and E, so we can club them as AE or EA. We consider them as a group. Now the remaining 5 letters plus this group is 6 letters actually, if we take this group as one single letter. So there are 6 letters and they can be arranged among themselves in 6 factorial ways. Now the group can be AE or EA, so they can be actually arranged among themselves in 2 factorial ways. So the total number of words become 6 factorial into 2 factorial, that is equal to 1440. Now the C part, that is T occupies the 4th position. So the words will be of this form, T being at the 4th position, and the rest of the places can be filled by the remaining letters, that is B, R, A, C, E and K. So they can be done in 6 factorial ways, that is the total number of words equal to 6 factorial to 720. Now students, let's move on to the next very important part of this lecture, that is combination. Combination refers to the different number of selections that can be made selecting some or all of the given things from a set of things. Here it is important to note that the order of things within a group is not considered. Now this is the very marked difference between permutation and combination. In permutation, what we do is we are focusing on the arrangement of things, but in combination we focus only on the selection of things from a set of things. For example, let us say that we have got a bag that has got 6 different balls. Now what we have to do is we have to select or pick 3 different balls from this bag containing 6 different balls. Here what we are doing is we are just selecting the 3 balls out of the 6 without worrying about the order of balls. That is, it is not important which ball comes first and which ball comes second or which ball comes third. What we are only concerned about is that we have to select 3 balls out of those 6 different balls. Now any combination is denoted by NCR. Now NCR is equal to n factorial divided by r factorial into n minus r factorial, and that is equal to NPR by r factorial. As we know that n factorial by n minus r factorial is equal to NPR, so we can write NCR is equal to NPR divided by r factorial, or NPR is equal to r factorial into NCR. Now what does that mean? It means that NPR is equal to r factorial into NCR. So what we can say is permutations denote 2 steps, that is, first step is selection of things and then arranging them. So r factorial represents the arrangement of things and NCR represents the selection of things. Once again I would say that permutation represents 2 steps, first selection of things and then arrangement of those things. Here NCR represents the selection of things and r factorial represents the arrangement of those things. Now n factorial is equal to n into n minus 1 into n minus 2 up to n minus r into n minus r minus 1 up to 3 into 2 into 1, and this when divided by r factorial into, when we expand n minus r factorial we get n minus r into n minus r minus 1 up to 3 into 2 into 1. So we see that n minus r into n minus r minus 1 up to 3 into 2 into 1, and this n minus r into n minus r minus 1 up to 3 into 2 into 1 gets cancelled out. and what we get is NCR is equal to n into n minus 1 into n minus 2 up to n minus r plus 1 whole divided by expansion of r factorial, that is r into r minus 1 into r minus 2 up to 3 into 2 into 1. Now some of the important points to note are NC0 is equal to 1, NCN is equal to 1 and NC1 is equal to n. Also NCR is equal to NCN minus r. The third point is NCR plus NCR minus 1 is equal to n plus 1 CR, and if NCX is equal to NCY, then we can say that x is equal to y or x plus y is equal to n. Why does it happen? When we see this second condition, NCR is equal to NCN minus r, from here we can conclude that either x is equal to y or x plus y is equal to n. Now one more important property is NCR upon NCR minus 1 is equal to n minus r plus 1 whole divided by r. Now let's try to look at some of the important deductions on combinations. Now case number 1. The number of selections from n different things taken r at a time when k particular things occur is n minus k c r minus k. Now let's try to see why does this happen. Let us say we have got n things, that is we have n things. These are in total n things, and let us say these are k things, and they have always to be together and they have to be selected all the time. For all the selections, these k particular things have to be present. And let us say we have like r things need to be selected. So what we see is these k things will always be there. Now the remaining r minus k things have to be selected from the remaining n minus k things. So the number of combinations become n minus k c r minus k. Now let's take another case where the number of selections from n different things taken r at a time when k particular things never occur is n minus k c r. Now what we have to do is we have to find the number of selections from n different things, and we need to take r at a time when k particular things never occur. So again we'll try to see why does this happen. Let's say we have k things that are never selected and we have got n things. Let these be the n things. These are the n things from which we have to select. And let us say there are k things, some k things that are never to be selected. So what we have is n minus k things that need to be selected. Now, and we need is r things. Here we need r things. So what we are going to do is we are going to select out of these n minus k things r things. Thus the number of selections become n minus k c r. Now let's study one more important case on the theory of selections, that is the number of ways of selecting at least one thing out of n different things. So it means that we have got n different things and we are to find the number of ways of selecting at least one thing out of those n different things. Now this is equal to nc1 plus nc2 plus nc3 up to ncn minus 1 plus ncn, and that is equal to 2 to the power n minus 1. Now how do we derive at this result? We have got n different things, so at least one thing we have to select at least one thing out of those n different things. If I say that I select one thing, how can I do that? It can be done in nc1 ways. If I say I want to select two things, then it can be done in nc2 ways. Similarly, three things in nc3 ways, n minus 1 things in ncn minus ways, and n things in ncn ways. So the total number of ways of selecting at least one thing would be equal to summation nc1 plus nc2 plus nc3 up to ncn. Now from binomial theorem, we know that nc0 plus nc1 plus nc2 up to ncn is equal to 2 to the power n. We also know that nc0 is equal to 1, which we have already studied. Thus we can say that nc1 plus nc2 up to ncn is equal to 2 to the power n minus 1. Again, the number of ways of selecting at least one thing out of n different things is equal to nc1 plus nc2 up to ncn, and that is equal to 2 to the power n minus 1. Now we have one more way of looking at the same problem or at the same case. Let us say we have got n things and we need to choose how many things? At least one thing. Let's consider the first thing. We have got two choices for it. Either we can select that object or we cannot select that object. So there are two cases for this particular thing. For the second thing, again we have got two choices. Either we select it or we don't select it. For the third object, we have again two cases. Either we select it or we don't select it. So for all those n objects, the total number of choices for us would be 2 into 2 into 2 up to the n things, that is equal to 2 to the power n. Now this also includes the particular case where none of the objects is chosen or none of the object is selected, but we want at least one object to be selected. So what we do is we subtract the case where none of the object is selected from the total number of cases. So 2 to the power n minus 1 is the number of ways of selecting at least one object out of the n given objects. Once again I would say that let us consider n objects. Now from those n objects, let's consider the first object. It has got two choices. Either it can be selected or it cannot be selected. Similarly, for the second object there are two choices. Either it is selected or it is not selected. Similarly, for the third, fourth up to n. So in all, the total number of choices is equal to 2 to the power n. But it also includes the case where none of the object is selected, but we want at least one object has to be selected. So we are going to subtract the case where none of the object is selected from the total number of selections, and that is equal to 2 to the power n minus 1. Now we have studied some theory on combinations or selections and derived some important results. Now what we are going to do is apply those theories and apply those deductions in solving some problems. So let's see this IIT JEE 1995 problem. 7 relatives of a man comprises 4 ladies and 3 gentlemen. His wife has also 7 relatives. 3 of them are ladies and 4 gentlemen. In how many ways can they invite a dinner party of 3 ladies and 3 gentlemen so that there are 3 of man's relative and 3 of wife's relatives? So what we have been given in this question is, there is a man who has got 7 relatives, of whom 4 are ladies and 3 gentlemen, and wife has also 7 relatives, out of which 3 are ladies and 4 gentlemen. Now they have to invite for a dinner party, and we need to find the number of ways in which they can do so. The constraint is that there are 3 ladies and 3 gentlemen, and those 3 have to be man's relative and 3 of wife's relatives. So let's try to solve this problem. The man has got relatives, out of which there are 4 ladies and 3 gentlemen. For wife there are 3 ladies and 4 gentlemen. Now for inviting for a dinner party, and in which there has to be 3 ladies and 3 gentlemen, and 3 relatives of man and 3 relatives of wife, there are actually 4 number of cases. Let's see them. First is, a man invites 3 ladies, his relatives, and the wife invites 3 gentlemen. Second, man invites 3 gentlemen and the wife invites 3 ladies. Man invites 2 ladies and 1 gentleman, and the wife invites 1 lady and 2 gentlemen. And the fourth case is, man invites 1 lady and 2 gentlemen and the wife invites 2 ladies and 1 gentleman. Again, we would like to see that there are 4 cases in all. The first is, man invites 3 ladies and wife invites 3 gentlemen. Man invites 3 gentlemen and wife invites 3 ladies. Third case being, man invites 2 ladies and 1 gentleman and the wife invites 1 lady and 2 gentlemen. And fourth, man invites 1 lady and 2 gentlemen and wife invites 2 ladies and 1 gentleman. Now for case number 1, we have 4c3 into 4c3 equal to 4 into 4, and that is equal to 16. For case number 2, 3 ladies have been invited and 3 gentlemen have been invited out of 3. So we have 3c3 into 3c3. For the third case, out of 4 ladies, 2 ladies have been invited by man, and out of 3 gentlemen, 1 gentleman has been invited by man. Similarly, the wife invites 1 lady out of 3 ladies and 2 gentlemen out of 4 gentlemen. This can be done 6 into 3 into 3 into 6, that is equal to 324 ways. For the case 4, out of 4 ladies, man invites 1 lady, that can be done in 4c1 ways. This, and out of 3 gentlemen, 2 gentlemen have been invited in 3c2 ways. For the wife, out of 3 ladies, 2 ladies have been invited in 3c2 ways, and for wife, out of 4 gentlemen, 1 gentleman has been invited in 4c1 ways. So that is equal to 4 into 3 into 3 into 4, that is equal to 154. Hence, the total number of ways equal to 16 plus 1 plus 324 plus 144 equal to 485. Now let us see another very interesting problem on selections. Find the total number of 5-letter words that can be formed using all the letters of the words differentiation. So in this problem, what we have to do is, we have to find total number of 5-letter words and we have to use all the letters of the word differentiation. So how we are going to do it? How we are going to approach to this problem? Let's see. Differentiation is a 15 letters word. It has got 3 I's, 2 F, 2 T, 2 E, 2 N, 1 R, 1 A, 1 D and 1 O. So what we see is, we have got 9 different letters and there are 5 sets of similar letters. These 5 sets are I, F, T, E and N. So let's see the different cases that arise in this problem. Case number 1, all the letters are different. So we are going to have such words where all the letters are different. So let's calculate it. The total number of such words is equal to NC5 into 5 factorial. Now what we have seen is, there are 9 different letters and we need 5-letter word. So what we do is, we select 5 letters out of those 9 different letters in NC5 ways, and then we arrange them or permute them in 5 factorial ways. So the total number of such words is equal to NC5 into 5 factorial. Now the second case is words of the kind where 2 letters are alike of one kind, 2 letters alike of another kind and 1 different letter. So it is somewhat of the form XXYYZ, where XXYY are similar and Z is different. So such number of words are 5c2 into 7c1 into 5 factorial by 2 factorial into 2 factorial. How does this come? This is through we select 2 such sets of alike characters from a set of 5 characters. We have already seen there are 5 sets of similar letters. We select 2 such set from that, and then we are left with 7 different letters. So we select 1 different letter from those 7 different letters in 7 C1 ways. Now this is about selection. Now we have to arrange them. Now we know that there are 2 sets of similar letters. So they can be arranged among themselves in 5 factorial by 2 factorial into 2 factorial ways. So as such, the total number of such words become 5C2 into 7C1 into 5 factorial by 2 factorial into 2 factorial. Now the third case is 2 letters alike and 3 different. It is somewhat of the form AA, B, C, D. That is, 2 letters are alike and the 3 are different. This can be done in 5C1 into 8C3 into 5 factorial by 2 factorial. Why? Because out of those 5 sets of similar letters, we select one set, and then we are left with 8 different letters. Out of those, we select 3 different letters in 8C3 ways. Now 5C1 into 8C3 is the selection part. Now we have to arrange them. This can be done in 5 factorial by 2 factorial. We are dividing it by 2 factorial because there are 2 similar letters in those 5 letter words. Now the fourth case, 3 alike letters and 2 different letters. It is somewhat of the form AAA, BC. Here there are 3 alike letters and 2 different letters. Now the total number of such words is equal to 1C1 into 8C2 into 5 factorial by 3 factorial. Why? Because we only know that there are 3 I's that occur in differentiation and no other letter occurs more than 2 times. So the only 3 letters that we can choose is I. This can be done in 1C1 ways. Now the remaining 2 positions have to be filled by 2 different letters, and those are 8 in number. So selection of those 2 different letters is in 8C2 ways. Now 1C1 into 8C2 is the selection part. Now we have to arrange them. That can be done in 5 factorial by 3 factorial. 3 factorial because there are 3 I's, 3 similar I's in those 5 letter words. The last case is 3 alike letters of one kind and 2 alike of the other kind. That is, it is of the form AAA, BB. So again, those 3 letters can only be I, and the remaining 2 alike letters can be chosen from the set of similar letters that are 4. Now because I has been chosen, now we have 4 left. Now out of those 4 sets of similar letters, we choose one set. That can be done in 4C1 ways. Now we have to arrange them also. That can be done in 5 factorial by 3 factorial into 2 factorial. 3 factorial because there are 3 I's, and 2 factorial because of those other similar letters. So in all, the total number of words is the summation of all the number of words that we have calculated for all the 5. Now let's solve this last IIT JEE problem, which appeared in 1987. A student is allowed to select at most n books from a collection of 2n plus 1 books. If the total number of ways in which he can select at least one book is 63, find the value of n. Now what we have been given in this question is, we have a total of 2n plus 1 books, and a student is allowed to select at most n books. That is a maximum of n books he can select. Now it is given that the total number of ways in which he can select at least one book is 63. So we have been given the clue that the number of ways in which he can select at least one book is 63. So according to that, we have to solve and find the value of n. Now what have been given is, number of books is equal to 2n plus 1. The maximum number of books that a student can take is equal to n, and the total number of ways he can select at least one book is 63. This is the information that is given to us. Now we know that number of ways of selecting at least one book is 63, and the student can take at most n books. So what we can say is 2n plus 1 C1 plus 2n plus 1 C2 up to 2n plus 1 Cn minus 1 plus 2n plus 1 Cn is equal to 63. We haven't extended n up to 2n plus 1 because the maximum number of books a student can take is n. Now from binomial theorem, we know that 2n plus 1 C0 plus 2n plus 1 C1 up to 2n plus 1 C 2n plus 1 is equal to 2 to the power 2n plus 1. This result comes from binomial theorem. Also we know that 2n plus 1 c0 plus 2n plus 1 c1 up to 2n plus 1 cn is equal to 2n plus 1 cn plus 1 up to 2n plus 1 c 2n plus 1. So this term is equal to this term. Thus we can say that 2n plus 1 c1 up to 2n plus 1 cn is equal to 2 to the power 2n minus 1. Why? Because we divide 2 to the power 2n plus 1 by 2 because both those terms were equal. So, and also 2n plus 1 c0 is equal to 1. So thus we get 2n plus 1 c1 up to 2n plus 1 cn is equal to 2 to the power 2n minus 1. This we know that this is equal to 63 according to the question. So 63 is equal to 2 to the power 2n minus 1, or we can say 2 to the power of 2n is equal to 64, or we can say n is equal to 6 by 2, that is 3. This is the end of our lecture 1 on permutations and combinations. I really hope you had a wonderful learning experience. For more clarity and more understanding of the theories explained in this chapter, try solving as many problems as you can. For more doubts and queries, visit our website www.TopIITcoaching.com. We are perfecting IIT preparation. Thank you.